In this specific room, the digital thermostat locked on the wall clearly displays 23 degrees Celsius. The indoor air is perfectly still, mechanically filtered, and flawlessly comfortable against your skin. But the thermal energy that was just removed from this enclosed space did not simply disappear into the void. It was only relocated to a different address. An elaborate mechanical system had to physically capture and transport that specific volume of heat outward through a network of copper pipes. A heavy compressor utilized a significant amount of electrical power to force that continuous movement. And out on the pavement, the surrounding city continues to release its own stored thermal energy into the atmosphere long after the sun has set. A dedicated climate study focusing specifically on Dubai recorded that the average nighttime urban heat island intensity was about 3.3 degrees Celsius higher than the surrounding rural areas during their research period. That specific measurement reveals a fundamental paradox of modern urbanization in extremely arid environments. Is Dubai actually eliminating heat, or is it merely transferring that thermal load from the isolated spaces where people live to the exact public streets where the city must absorb it? If that original unit of heat never truly vanishes, we have to pause and ask a much larger question. Where exactly is all that displaced energy going? To successfully answer that question, we first need to look closely at how modern comfort is mechanically produced inside a building. Air conditioning does not create coldness as some sort of new physical substance that can be pumped into a room. The technology operates precisely like a heat pump. The indoor unit draws warm ambient air across a series of highly chilled coils. A specialized chemical refrigerant captures that thermal energy and carries it away from the living space. Then the mechanical compressor, which requires a massive amount of continuous electrical power, forces that refrigerant to move rapidly through the entire closed system. Finally, the exterior condenser unit exhausts that collected thermal energy out into the surrounding outdoor environment. The heat expelled outside into the street is not just the original warmth taken from your bedroom or office. It is the absolute total combination of the heat removed from the building plus the mechanical energy used by the compressor to keep the entire thermodynamic process running. This is the exact point we almost always overlook when we adjust the digital thermostat on the wall. That glowing screen showing 23 degrees Celsius only describes the cooled side of the mathematical equation. It tells you absolutely nothing about the physical space that just received the rejected thermal load. A single air conditioning unit, operating on a single apartment balcony, cannot alter the climate of an entire neighborhood. The atmosphere is massive enough to absorb that tiny thermal exchange without any measurable consequence to the street below. But what happens when an entire metropolitan district operates thousands of these heavy cooling systems at the exact same time? Before the very first cooling unit even turns on for the day, the urban environment is already acting as a massive thermal reservoir. Throughout the peak daytime hours, intense solar radiation strikes the glass facades, the structural concrete walls, the flat rooftops, and the endless miles of asphalt roads. A specific portion of that incoming solar energy is immediately reflected back into the upper atmosphere. But a massive percentage of that heat is absorbed directly into the physical structure of the city itself. These incredibly dense construction materials heat up and begin storing that solar energy deep within their heavy mass. When the sun finally sets over the horizon, the ambient air temperature might begin to drop, but the physical city does not instantly cool down. Those concrete and asphalt surfaces continuously transfer their stored heat back into the surrounding night air for hours on end. This delayed release of energy is a primary reason why highly built-up urban zones can cool down much slower than the open desert or the rural outskirts. You do not need to look at an advanced infrared camera to understand this delayed thermal reaction. You can feel it physically when you walk across a paved parking lot or stand near a concrete wall late at night. The invisible heat continues to radiate upward from the asphalt long after the sky has gone completely dark. But the physical properties of building materials only explain why the heat stays trapped in the city. They do not fully explain why certain blocks and specific neighborhoods struggle to release that heat much more than others. The physical shape of a neighborhood creates its own distinct and localized microclimate. Urban morphology, which includes the height of the buildings and the physical spacing between them, directly influences how thermal energy behaves at the ground level. The specific geometry of a street can dictate exactly how much protective shade touches the pavement during the hottest parts of the day. It also dictates the exact pathways that natural wind can follow as it moves through the commercial or residential district. Surfaces that face different geographical directions will absorb and reflect heat in highly varied ways throughout the afternoon. A massive residential tower might successfully protect the pedestrian sidewalk below from direct sunlight. But that same towering structure can simultaneously block or alter the natural ventilation patterns that would normally help flush warm air out of the street level. This architectural reality means that not every single district across Dubai experiences the exact same thermal conditions. A densely packed commercial center will manage heat very differently than an open residential community with wider streets and lower rooflines. The architectural layout can either trap the radiating warmth like a canyon or allow it to successfully dissipate into the cooler upper atmosphere. However, Dubai is not merely holding on to the heat delivered by the Arabian sun. The city is also actively generating an entirely separate stream of thermal energy through its own daily operational mechanics. This is precisely where the cooling infrastructure begins to interact with the physical shape of the city. While one individual machine does not change the local weather, a modern metropolis operates an astronomical number of cooling systems simultaneously. Every single residential tower, luxury shopping mall, corporate office complex, and underground transit station is pulling heat from its interior spaces. All of those interconnected mechanical systems are using electrical energy to transport that collected heat away from human occupants. And all of them are ultimately exhausting that combined thermal load into various exterior locations across the city blocks. This artificial exhaust becomes a new layer of anthropogenic heat that stacks directly on top of the energy already being released by the concrete and asphalt. To understand this hidden mechanism, scientists have modeled the localized effects of air conditioning exhaust in other hot and arid urban environments like Phoenix. Those specific scientific models demonstrated that rejected heat from massive cooling infrastructure could indeed influence nighttime urban temperatures under specific atmospheric conditions. We must be very precise here about the boundaries of this evidence. That specific study from Phoenix is not a direct physical measurement of Dubai. The resulting data cannot be universally copied and pasted onto a completely different city with different coastal humidity levels and different natural wind patterns. The public data currently available is simply not sufficient to tell us exactly how many fractions of a degree Dubai's temperature rises solely because of air conditioning exhaust. But the underlying physical mechanism remains entirely valid and widely recognized by climate researchers worldwide. When millions of machines dump excess thermal energy into streets that are already radiating stored solar heat, the local environment inevitably absorbs that extra burden. This physical reality sets the stage for a much more complicated engineering problem. When the ambient temperature outside begins to steadily rise, how exactly does the mechanical cooling system respond to that changing environment? This physical reality creates a highly localized feedback loop within the urban core. The urban surfaces absorb and store massive amounts of thermal energy throughout the peak daylight hours. The heavily built environment then cools down very slowly after dark, due to its immense thermal mass. Because the outside air remains warmer than it naturally would be, the mechanical cooling systems must transport a heavier thermal load to maintain the exact same indoor comfort. To move that extra heat, the building compressors are forced to draw additional electrical power from the central grid. The entire cooling process then exhausts both the interior heat and that extra mechanical energy back out into the urban environment. The streets and building facades receive that additional rejected energy. And the required cooling work can continue to gradually increase as the thermodynamic cycle repeats itself night after night. This loop does not need to cause a catastrophic grid failure to become a serious economic and technical issue for the city. It simply means that providing the exact same level of indoor comfort will steadily demand a little more electrical capacity, a little more heavy infrastructure, and a little more heat that must be physically moved. We can see the sheer scale of the energy required by looking at the official utility data. The peak electrical load for Dubai in the year 2025 reached 11.39 gigawatts. That specific figure represents an increase of 5.83% compared to the peak load recorded in the year 2024. We must absolutely put that massive number into its proper context. That figure represents the total electrical demand for the entire city across all sectors. Population growth, new construction projects, and expanding economic activity are major drivers behind that rising power consumption. The data does not prove that the urban heat island effect is solely responsible for that total increase in demand, but it forces us to ask a highly critical question about the future of urban engineering. Within that growing peak demand, how much electrical work is being spent simply to fight against the thermal energy that the city itself has trapped or redistributed? But at this exact point in the investigation, we are in danger of jumping to a very simplified conclusion. The most common reaction is to point directly at the cooling infrastructure and label it as the primary villain of the climate story. That conclusion is both technically flawed and practically useless. Air conditioning is a non-negotiable foundation of modern infrastructure in this specific geographic climate. Simply turning off the cooling systems would not magically solve the underlying thermal structure of the city. It would only remove the single most important layer of physical protection that human beings have against extreme environmental stress. The mechanical cooling units are only one component of a much larger, highly complex urban system. The density of the buildings, the choice of construction materials, the flow of heavy traffic, and the natural coastal humidity all play massive roles in shaping the microclimate. The correct question to ask is not whether Dubai should use air conditioning to protect its residents. In this harsh desert environment, abandoning mechanical cooling is simply not a realistic or safe option. The correct question is how much heat the city must generate and transport just to maintain its current standard of livability. Dubai has not ignored this challenging engineering reality. The government has successfully implemented strict green building regulations and the comprehensive Al-Safat certification system. There are mandatory technical requirements governing glass performance, thermal insulation, and solar heat gain to ensure buildings resist the climate more effectively. The city does not merely rely on plugging in more machines to solve the problem, but if Dubai already possesses better building codes and more efficient cooling technology, why could the total demand for energy still continue to climb? The answer lies in how the city has chosen to upgrade its thermal infrastructure on a massive scale. Dubai does not lack highly efficient cooling technology. The city has actually pioneered the deployment of immense district cooling networks on a scale rarely seen anywhere else in the world. Instead of forcing every single residential tower to operate its own independent chiller on the roof, a central plant generates chilled water for an entire neighborhood. This chilled water is then distributed through an extensive underground pipeline network directly into multiple surrounding buildings. By centralizing the production of cold water, the operators can optimize the electrical load, upgrade the heavy equipment more easily, and maintain the machinery at peak performance. Under the right operational conditions, this centralized approach has the potential to reduce the energy used for cooling by up to about 50% compared to some traditional air conditioning methods. It is absolutely vital to note that this percentage is a maximum potential target, not a guaranteed absolute result for every single connected project across the city. But it proves that the engineering philosophy has fundamentally shifted towards serious system optimization. The city has built infrastructure that treats cooling as a shared district utility rather than an isolated problem for each individual property owner to solve alone. This represents a massive technical victory in the ongoing fight against urban heat. But improving the energy efficiency of a single cooling unit is not the final answer to the citywide problem. This is the pivotal turning point of the entire investigation. The specific efficiency of one isolated system cannot adequately describe the thermal performance of an expanding metropolis. A newly constructed corporate tower might use significantly less electricity per square meter than a building constructed 20 years ago. However, the total floor area that requires continuous climate control is expanding every single year. The residential population is growing, new commercial districts are being developed, and the baseline expectations for absolute thermal comfort are constantly rising. Therefore, the total aggregate demand for cooling can easily increase even if the specific energy intensity of each new building goes down. Let us look at a purely illustrative scenario to fully understand this mathematical trap. Imagine a next-generation cooling system that successfully uses 20% less electricity to cool a standard apartment unit. That is a legitimate engineering triumph that should be celebrated. But if the total number of apartments requiring that cooling service grows by 30%, the absolute demand placed on the central power grid will still go up. This is an illustrative example meant to explain the mechanical concept, not measured operational data from Dubai. But the underlying principle reveals a fascinating reversal in our understanding of urban energy dynamics. Two statements can be entirely true at the exact same time. Dubai is cooling its interior spaces more efficiently than it ever has before. And Dubai might still require more total energy to accomplish its massive cooling goals. The technical performance of a building is measured by the digital sensors inside the isolated mechanical room. But the true efficiency of a city is physically felt by a person walking down the sidewalk. When someone leaves a perfectly chilled shopping concourse, walks through the revolving glass doors, and steps out into the street, the hot and humid air instantly clings to their skin. They are standing in a space that has absorbed the rejected heat from the exact building they just exited. Is the only way forward to build larger cooling plants, or is there a way to reduce the amount of heat that must be processed in the first place? To break the feedback loop, urban planners must intervene at three distinct points in the thermal cycle. The first experiment focuses squarely on reducing the amount of heat that enters the system. This means deploying exterior shading devices, upgrading wall insulation, and carefully orienting building facades to avoid direct afternoon sunlight. It involves utilizing advanced glazing technology to minimize solar heat gain through the massive glass windows. The core question here is how much thermal energy can be physically blocked before it ever becomes a job for the mechanical cooling system to resolve. The second experiment focuses on transporting the unavoidable heat much more efficiently. This involves expanding the district cooling networks and mandating high-performance chiller units across all new developments. It also means implementing smart load controls, utilizing off-peak thermal storage tanks, and setting rational indoor temperatures to avoid overcooling. The question here is whether the system can use significantly less electrical power to move the exact same volume of thermal energy. The third experiment requires fundamentally changing the physical microclimate of the neighborhood itself. This strategy pushes beyond the walls of the individual building to introduce continuous pedestrian shading and optimized wind corridors. It relies on planting climate-appropriate vegetation that manages water resources carefully and selecting paving materials that do not trap excess solar radiation. The primary goal is to prevent a portion of that solar energy from becoming an urban heat problem at the street level. A technological solution only demonstrates true systemic power when it reduces the total volume of heat that must be handled. If a technology merely shifts the thermal burden from the inside of a building to another side of the system, the underlying problem remains completely unsolved. So, is Dubai trapped in a cycle of artificially heating its own environment? The final answer must be carefully divided into the things we can prove and the things we cannot safely conclude. The scientific evidence confirms that Dubai experiences a noticeable nighttime urban heat island effect. The physical materials and the shape of the neighborhoods directly influence how thermal energy is stored and eventually released. We also know, as a matter of physics, that mechanical air conditioning moves heat and consumes electricity to perform that work. And the official utility data proves that peak electrical demand continues to grow alongside the rapid expansion of the urban footprint. The city has actively responded by deploying serious energy efficiency regulations and massive district cooling infrastructure. However, the available public data does not allow us to calculate exactly how many degrees the city temperature rises, specifically due to cooling exhaust. We cannot claim that air conditioning is the sole cause of the urban heat island, nor can we claim that the electrical grid is on the verge of a sudden collapse. The city is not a single uniform climate zone, and there is absolutely no evidence that this feedback loop has become mathematically irreversible. But a clear editorial verdict remains. Dubai is not just fighting against the natural heat delivered by the desert sun. The city is simultaneously forced to manage the additional thermal energy that its own urbanization process is storing, redistributing, and generating. The metropolis has not fallen into a catastrophic spiral that it cannot escape. But it is currently facing a highly unforgiving mathematical reality. The overall efficiency of the thermal infrastructure must increase significantly faster than the sheer scale of the spaces that require cooling. Let us return to the image where we started this investigation. In this quiet room, the digital thermostat still confidently reads 23 degrees Celsius. The mechanical systems have successfully completed the exact job that human comfort demanded. They flawlessly extracted the unwanted thermal energy from the enclosed living space. But the fundamental laws of thermodynamics dictate that heat does not simply vanish when the heavy glass door slides shut. A truly climate-adapted city is not just a settlement that possesses enough heavy machinery to keep its interior spaces adequately chilled. It is a city designed to generate and trap far less heat that requires moving in the first place. The engineering challenge of the next decade will not be fought inside the isolated mechanical rooms, but out on the open pavement. Inside, the room remains perfectly comfortable. But on the other side of the wall, the heavy bill for that comfort is still being passed forward. This video is produced for educational and analytical purposes, examining urban thermal dynamics and infrastructure systems. The precise contribution of mechanical exhaust to local temperatures varies, and certain scenarios presented are illustrative models, rather than exact measurements of current conditions in Dubai. How do you think rapidly growing cities should solve the balance between indoor comfort and outdoor temperatures? Share your perspective and join the discussion in the comments below. If you found this investigation valuable, please subscribe to the channel for more analytical deep dives.